So this is the Unified Modeling Language lecture. And what we are going to discuss this afternoon is on a language for modeling that is being used. It's called Unified Modeling Language, and it's being used a lot for project development and system design, mostly in computer science. But it's also a language that can be applied to other type of complex system development, not only computer science type of development. And that's what we're going to do today. I'm going to show you some different diagrams that could be very helpful in defining some of the areas of your system. So these are some references. There's a lot of information about UML diagrams in the literature and also online. You can go to YouTube. There's a lot of information out there. Actually, most of these software packages that have some type of environment for diagrams, most of them will have a package or a template for UML. Okay, so you don't have to necessarily build this from scratch. There's our template packages that are already built for UML. So UML is a language for visualizing, specifying, constructing, documenting the artifacts of a software-intensive system. So as I mentioned, this is originally used for software-intensive system design, but this has been transitioning to not only software-intensive systems, but any type of system. So this is a standardized specification language for object modeling. It's a general purpose modeling language with graphical notation used to create an abstract model of a system. Originally defined by the object management group. And what are the things in the UML? There's structural things. These are mostly static parts of a model. These are called classifiers. That could be a class, an interface, a collaboration, a use case, active class, component, artifact, so on. So these are structural things that are mostly static. And they're behavioral things. These are dynamic parts of UML models like interactions, state machine diagrams, activity. So those causal loop models, they are represented differently, but there's an idea. We call them state machine diagrams here in the UML. There's also grouping things like a package, commenting things like explanatory parts of UML. You can create notes within the diagram. There's some different type of relationships that are used, different type of arrows, connectors. So here I have three. This is called dependency, right? That we have the dotted arrow. Is a relationship between two things in which a change to one thing, which is the independent thing, may affect the other thing, which is the dependent thing. So if you change this one, that will impact this one. This is the independent thing. This is the dependent one. So if you change this one, that will impact this one. An association is a structural relationship that describes a set of links. So association, they're basically some connection between the two, right? Some type of association that could go in both directions. And a generalization is a relationship in which the specified element, the child, builds on the specification of the generalized element. So how many of you are familiar with object-oriented programming? Object-oriented programming, nobody? Yes. Java, yes. Yes. So Java, C#, C++, those are object-oriented. So basically the idea of object-oriented is that you are able to reuse your code, right? So initially, I guess most of the people will code and will write lines and lines of code. And then if you want to use that code to represent a different system, you might need to, maybe it's easier for you sometimes to start from scratch, right? because reusing that code will require you to go to every line and make sure that you change the things that are. So that's what the object-oriented programming is trying to avoid. Like instead of writing lines of code one after the other, you write code, but each group of code you can label as an object, right? And then if you need to reuse a code, you can just call that object, which has those instructions. And then by calling those objects, you can reuse that code, right? So no, exactly. So when you talk about generalization, let's say you have something like you created a code for, and this is just a simple example, but I think it's powerful. You have a tree, right? And the tree could be orange. You can give you orange, strawberries, orange, any type of fruit, right? And then you can have a code that is describing or providing the functions for a tree. And then if you want to code in, let's say, an apple tree, you can reuse all the functions from the tree and just add some additional functions that are just used for an apple tree. Or you can use the same code to write a code for orange tree, right? And then in that way, you're reusing all the code that was already prepared for the tree. You're calling from that one and then adding some new information to the specific case. So that's the whole idea. When they say generalization, a relationship in which the specialized element, the child, that will be the apple tree or the orange tree, is built on the specialization of a generalized element, which is the tree, right? So that's the whole idea. And that's what we are trying to illustrate in some of these diagrams. Like you don't have to build everything from scratch. Like in our case for the system, I said that you can have an overlap between subsystems, like half of the system could be the same, 75% of the system could be the same. So you're reusing that part or that portion of the system and then just specializing some of the areas of the system. So we can illustrate that with UML. So there are 13 different type of diagrams, and the following picture provides a way to categorize them hierarchically. So there's structure diagrams and behavior diagrams. For our case, I'm going to be focusing for this class on those that are highlighted in red. So only one structure diagram, which is the class diagram, and multiple behavior diagrams, activity, use case diagrams, state machine diagrams. And then for the interaction, we have the sequence diagrams. So the rest of the lecture basically is going to just show you the different type of diagrams, what they are, how they're built, and some examples. So we'll start with the use case diagrams. These ones are describe the functional behavior of the system as seen by the user. Second diagram is the class diagram. This describes the static structure of the system. Like if you want to, for example, represent the different subsystems for your development, you can use a class diagram. Sequence diagram is for dynamic behavior, which is basically showing the interactions, how they move in terms of time, what are the things that are happening in your system. State chart diagrams also for dynamic behavior. This is similar, looks like a causal loop model. And the activity diagrams, this is more like a flow chart. Model the dynamic behavior of a system, in particular, the workflow. Okay, so let's start with the use case. Again, these are, once you start looking at these diagrams, you'll see, oh, those are simple. Yes, the answer is yes, they're simple. Building the diagrams is not difficult. I think the challenge is coming with the right scenario that you want to represent with the diagrams. So a use case is a model of system functionality. It's a description of the functionality of the system and its environment. This is typically used during the requirements elicitation to discover requirements and to represent the external behavior. So what we are doing with this use case diagrams is to try to understand how your stakeholders are going to be interacting with your system. And that can help you identify some additional requirements for your system. And they're very easy for the user to understand. So typically we have two main components for a use case diagram, the actor and the use case. The actor could be, I mean, as long as it looks like a person, could be one of those simple diagrams, or it could be more elaborate like the one on the left. And then the use case is typically represented by that symbol. The two main components of a use case are the use case and the actors. The actors represent roles, that is a type of user of the system. The use cases represent a sequence of interaction for a type of functionality. And the actors are the ones that are triggering those functions, right? So those use cases are representing functions that the system must perform, and the actors are triggering. So an actor model an external entity which communicates with the system. So this is not necessarily a person. It could be, for example, if you're representing an HVAC system, that could be the AC and the heater. Still an actor is interacting with the overall HVAC system. Or it could be a person, it could be another system, a physical environment. So anything that could interact with your system. An actor has a unique name and optional description. So for example, a passenger or a GPS satellite. Those could be actions for you, actors for your system. A use case represents a class of functionality, so a function provided by the system as an event flow. Think of main functions a system performs. Those are cases of your system. So for example, if you have a phone or cell phone, a function could be place a phone call, receive a phone call, or use the scheduler. Those are functions. Each actor must be linked to a use case, while some use cases might not be linked to actors. Okay, so if you have an actor in the system, you have to have some type of interaction with your use case. So here's an example, right? As you can see here, there's two actors, right? It's the user and the cellular network. And the system that you're trying to represent is a cell phone, right? So you have the different functions that the cell phone can perform, and then you're trying to identify who is interacting with the cell phone. You see the user here is placing a phone call. So the arrow is going to that use case. The scheduler goes in both directions, so there's no arrow. And the receive phone call is basically going into the user, right? So the interaction can go in both directions. Same thing for the cellular network. You place a phone call, then you are connected to the network. If you receive the phone call, then you're connected to that use case. Use case diagram for library. So what are the functions of the library? They're listed here in the middle. Then you have, let's say, a member or student. You have the circulation clerk and the supplier, right? So purchase supplies for the library. And then the same thing. So how is the member interacting with the library? How is the circulation lane clerk interacting with the library, and so on? That makes sense, right? So when you're going through your definition of the functions, right, like we saw in that one of the documents, you can start thinking about, okay, so these are my functions. Who's going to be interacting? Maybe I can produce a use case to represent those interactions. Who are my main actors, right? You can place them into a use case. You can put those functions and then identify, okay, these actors interacting with these functions. And maybe you can observe that there's some requirements in your system that are not necessarily addressing some of those interactions. Use case diagram, extend relationship, linking an optional use case to a standard use case. So for example, if you register course, may have a register for special class. The optional use case extends the standard use case, and the standard use case can execute without the extend case. So this is what I'm referring to. So if you register for a class, you can have some use cases that are connected to that registration. And then maybe you have some interaction with the instructor here in terms of letting you into one of those courses. And here's the example of an HVAC system and showing you different, it's the same thing, right? But there's a different template. It represents the same thing. In which you have the heater, the AC, the functions that the HVAC system will perform, and how is the homeowner interacting. Again, very simple. I think the challenge is for your system, what are the functions, what are the actors, and then try to identify how are they connected. And I want to see some of those. I'm going to specify how many I need in the progress in the project final report. But before we get into that, I want to show you, like, I know you might not have access to Visio in your laptop, but you can get access to through some of the computers here in Ingram, like on the third floor or maybe in the makerspace. Like you can create. And then you can type here UML. Yes. So you see on the left side, there's the state machine, the use case. So you can build some of this pretty quickly using Visio. Yeah. I don't like the colors, so you can also change that to no fill. But if, I mean, what I'm trying to say is if you have a preferred diagram software, most likely that diagram software would have some type of UML environment that you can use to build your diagrams. Okay, so class diagram, these are structural diagrams. And these make use of some of the concepts in software, like for example, different type of content that you want to use in your code. So for example, if you're going to be using a name in terms of integer, purpose, integral number, and then the members. So that's the type of abstraction. An instance will be a member of that specific type, right? So if you have a set of integer values, you're basically calling one of those members. And then a class will be an abstraction in the context of object-oriented languages. It encapsulates both the state variables and the behavior methods. So what does that mean specifically? Here you go. So this is what a single class will look like. You will have a top, you have a name. In the middle, you have the attributes. And then at the bottom, you have the functions or the operations for that class, right? So if you start at the top, it's a bank account. You have the owner, the balance, and then the functions that you can perform for that class. So a class is an abstraction of a concept within a computer program. And again, as I stated already, these can be easily implemented not only in computer programs, but in other type of systems. It encapsulates the state or the attributes and the behavior. But the only mandatory information is the name. There's different relationships in class diagrams. For example, here we have two classes, flight and also the passenger, which in this case is a frequent flyer. So an association is one of those types. This denotes relationship between classes, represents the ability of one instance to send a message to another instance, and also is built to represent multiplicity, which means that you see those numbers next to the boxes. Those are representing the number, right? So in this case, it's 0 to 0, but you can have different indicators here. They're listed here in the table: 0 to 1, 1, 0, 1, n, 0 to n, 1 to n. So for example, if you have a flight that might have 100 passengers, you can use 100 next to passengers. Say, okay, one flight will have 100 passengers. That's what this is trying to illustrate. You can have one-to-one association. That's what this is represented. So one country has one city or capital city, sorry. A polygon might have multiple points. So one polygon have n points, one too many. Another relationship is called aggregation. So this is important for your design. Like if you're trying to illustrate the pieces of your subsystem, that's what this arrow is trying to represent. You see the diamond shape at the top of the arrow. That means that these parts together create this other class. You need the tailpipe and the muffler to combine them. You create the exhaust system. This is a special case of association denoting a consists of hierarchy. The aggregate is the parent class. The components are the children class, and is graphically represented as a clear diamond shape, as you can see there. And then we have the generalization, which is what we discussed in terms of the classes and the child and so on. So these children classes inherit the attributes and operations of the parent class, like we did for the tree, and then the apple tree and the orange tree. This is what the generalization is trying to illustrate. Simplify the model by eliminating redundancy. That's what we want to do. The UML graphical representation of a generalization is a hollow triangle shape. Class diagrams represent the structure of the system, and they are used during the requirement analysis to model problem domain concepts. And if you want to make a note or highlight this, I might ask you certain things from this slides, like when do you use the class diagram? Right there, during requirement analysis, to model the problem domain concepts, during the system design, and during the object design to model classes. So here's another example. Another example in terms of a company. So this is not necessarily a software, but this is representing the company. So you see the aggregation. So in order to get the company together, you need departments, you need office space. And then within the departments, you need multiple people. Like you have members and you have managers. All of them can be described using this person. And then the office is one. You have the I forgot the name, sorry. The generalization arrow right there, which is basically using some of the information from the office to create the headquarters. Another class diagram, this is connected to the HVAC system. So again, illustrating some of the components or subsystems for the HVAC. Any questions? Class diagram, simple, good. So again, reason I'm going through this, because you're going to be building some of these diagrams for your project. So we are going to touch base on this with the following lectures as well, but make sure that we have a good understanding of the different type of diagrams and how they are used. So sequence diagrams represent the system behavior in terms of interactions between the system entities. These complement the class diagram, which represents structure. It's useful to find participating objects. It's time consuming, but it's worth the investment. And it's good to create some system scenarios. Like, for example, if you try to mitigate risk, you can create these scenarios and illustrate, okay, if we do this and this happens, this is what's going to happen. So what is a sequence diagram? It's an interaction diagram that emphasizes the time ordering of messages. Graphically, is a 2D table that shows objects arranged along the x-axis and messages ordered in increasing time along the y-axis. So for example, here we have 3 objects. At the top, times is represented by that arrow going down. So what this is saying is message 1 happens first, message 2 happens next, message 3 happens next. And then as time moves down, the messages are also moving down. So here's a sequence diagram to represent the interaction of a passenger with the ticket machine. You're basically, again, looking at the passenger making some actions or taking some actions to the ticket machine, selecting the zone, inserting coins, pick up change, and pick up the ticket at the end. So in this case, you see there's a bar. This bar right here is illustrating continuous time. This one is illustrating this, selecting the zone takes this time and then done. This time, done. This time, done. So basically the user is waiting for those things to be completed to move to the next step. So that's the meaning of those bars. Classes are represented by columns. Messages are represented by arrows. Activations are represented by narrow rectangles. Lifelines are represented by dashed lines. Okay, so those are the lines that are connected to those activations. Here's another example. This is representing the interactions of the user with the watch. So you have the watch, the LCD displays, and the time. So this is basically illustrating the process of setting the time for that watch. You press button 1. The same simple watch showing blink hours is going to be showing in the LCD display. And then after that, you press a button, blink minutes, press another button, you increase the minutes, you refresh, and then you continue that process. Here's another sequence diagram of a teacher trying to log into a system, a computer system. So again, you can see what's going on here. Teacher is going in, either the user with the database goes back, and then after the successful logon, the lookup student, retrieve student information, get the information. And here's for the HVAC system. So we have presented the use case for the HVAC, the class diagram for the use for the HVAC, and this is the sequence diagram. Any questions? We're getting towards the end now. So state chart diagrams. State chart diagrams are shown this life cycle of an object. A state is a condition of an object for a particular time. An event causes a transition from one state to another state. So here's the state chart for phone line. So for example, if you were to represent the state chart of a single machine, you can say, okay, this machine will have two states, right? State one, busy, and then state two, idle. So if those are the only two states for the machine, you represent those states with the yellow boxes. And then you want to understand what will be the initial state of your system. Is it busy or idle? Most likely you're going to start idle, right? So to represent the initial state, you use this circle, which is the one that you are seeing here. You start idle. And then something needs to happen for you to move from here to here, from here to here. Okay, so let's say a part arrived to the machine. You have to process it. So you can have part arrival. That will make the machine go to the next state. And then part completed, go back to idle, right? So this is what the state chart diagram is trying to do, is trying to illustrate these are the different states for your subsystem or for your system. And this is how you're going to transition from this state to this state to this state to this state. Very important in terms of the design, because you want to make sure that you're covering all the bases, right? And if you identify that there's a interaction that is not happening or a state that is not considered, then you can revise your design and your requirements based on these diagrams. So here's a state chart diagram for fire. Yes, let's say a fire happening. You have an open incident. You notify the police, you notify the fire chiefs, and then you allocate resources. That's just to notify that a fire is happening. State chart for the heater in the HVAC system. In this case, you see the conditions. You go from cooler off to cooler on. If the temperature is above this cooler upper limit, you go to cooler on. If the temperature is less than limit, you go to cooler off. Same thing for the heater. Okay, one more, which is the activity diagram. And as I said, this one is more like a flow chart. Shows the flow control within a system. An activity diagram is a special case of a state chart diagram in which states are activities or functions. So if you're familiar with flow charts, these are very similar to a flow chart. You got the processes or the functions in this case, and then those diamonds are representing decision points, right? So depending on the decision that you make, you move to the one area of the flow chart or the other area of the flow chart. So that's the last one. So in summary, UML provides a wide variety of notations for representing many aspects of system development. Powerful but complex language is used in system modeling for model-based system design. And in this lecture, we'll describe some of the UML diagrams, including the behavior models, such as the use case diagrams, the structure object model, like class diagrams, and behavioral models, like sequence diagrams, state chart, and activity diagrams. Questions? So remember, let's go back to this